Strategies to maximize the reusability of the UVM test scenarios in SoC verification. The abstract: in today's large and complex system on a chip SoC, timely completion of functional verification is one of the most critical challenges, and reducing the verification turnaround time (TAT) is very crucial for a successful SoC product development. This paper represents a new UVM code structure and three-level class inheritance, so the first and second level class code can be completely reused without any changes, and only the third level class code need to be modified according to the target SoC product, ensuring the high code reusability. This paper provides an efficient flow for a complex and composite scenario development that contains the scenario definition in form of the metadata, secondary development of interpreter, and released metadata, and automatically generated test scenarios. The proposed approaches are able to shorten the scenario creation time by securing the high reusability through a test code structure optimization, and reduces the verification TAT by achieving target coverage with a small number of test scenarios through the efficient scenarios generation. Introduction. The importance of SoC design verification increases with the complex SoC designs. Functional verification consumes the deal with the time and manpower, and resulting in contributing a major role in the overall turnaround time (TAT) of SoC product development. Further, the highly competitive SoC product development in terms of the time to market poses a greater challenge in reducing TAT compared to the earlier product. To overcome these two approaches, the reducing simulation time for performing the test scenarios, and second is the shortening the test scenarios development period by increasing code reusability, have been asserted. This paper focuses on the second approach. The portable test and stimulus standard (PSS) and a representative solution based on the second approach has been developed and released by Axelera. PSS is a specification for expressing and creating the test scenarios and the stimulus for reuse in various verification platforms. Several studies confirm the effect of the code reusability in functional verification when using the EDA tools that support PSS. However, implementing reusable code directly during SoC verification with only this kind of tools have the following limitations, and they motivate the new approach which this paper proposes. PSS EDA tools usually focus on generating test scenarios by combining IP-level data manipulation tasks or sequences. However, in SoC verification, the system-level control operation scenarios are of greater importance than the data manipulation scenarios for each SoC component, because the majority of the design bugs occurred when implementing system control logic rather than integrating verified IPs. For instance, many EDA tools provide ARM architecture libraries such as cache, DVM, and low-power scenarios. The standard interface IP such as PCIe library, and the system modeling libraries include memories, processors, and more. The solve engine then generates multiple scenarios based on the user-defined constraint like target memory, region of the specific source IP, or data path reachability. This approach enables the various scenario developer to create multiple scenarios for fast coverage closure. However, the system control tasks including power and reset control are not provided by default and need to be manual coded. As a result, covering the combination of system control logic and data manipulation paths are tedious. In addition, PSS EDA tools mainly emphasizes code reusability across the multiple execution platforms such as simulator and emulator and post-silicon. It has the advantage to quickly secure the test scenarios for different platforms after scenarios are validated on one platform, typically simulation. On the other hand, it is more vital to secure simple test scenarios during the very early bring-up phase by reusing existing code, shift left, and extended them to the complex and composite ones, along with a sophisticated system control operation in order to detect design errors at the early development stage and consequently shorten the verification TAT. Hence, this paper targets code scenarios and reusability across the multiple products which are built in similar hardware architectures with this same execution platform. Finally, C code-based test. The basis for PSS are time-consuming in simulation since they run in real, bulky CPUs. For this reason, replacing a real CPU with a transistor is a very common technique in SoC verification. In addition, SoC verification is mainly performed using UVM-based system value, as it supports a predefined verification component, well-structured code, and superior control interpolation with multiple external events that are frequently used in system control operation scenarios. Accordingly, UVM-based test scenarios generation flows are more valuable than C code-based test. Recently, many PSS EDA tools are gradually expanding support for the UVM-based test scenarios generation, but cannot fully exploit the nature of the UVM because they still focus on the C-based test to reuse in multiple platforms such as emulation and silicon. So for the above region, this paper proposed a new approach to maximize the reusability of the UVM tested scenarios in SoC verification. To begin with, we structurally separate all the data manipulation code that are performed IP-specific operation and a system control code such as system reset, low power control, and general purpose I/O pad control, and because the former is likely to be reused. Based on this approach, we develop a new process to effectively combine them and implement complex composite scenarios. The Section 2 describes code structure that can separate data manipulation and system control based on reusability. Section 3 explains the process automatically to develop the complex and composite scenarios based on the well-structured code. Finally, Section 4 and 5 shows the achievement based on the experimental result of the product across multiple generations and summarizes the proposed method. Section 2 proposed code structure for the new approach. Typically, the test scenarios are made up of the IP functional operation code and a system level event and control code part. So the IP functional operation code could be the candidate for a reusable portion of assuming that the same IP could be integrated and entirely targeted to different SoC product. However, if the IP and system code is implemented within the same class, it's hard to identify and extract the reusable portion of code. This paper proposes a new UVM code structure to easily separate the IP-specific operation part of code and the test sequence from the system control code for future reuse. SV uses extensive object-oriented programming (OOP) techniques, and we have designed a class layering code structure based on the role by using inheritance and polymorphism concept of the OOP for code reuse. Figure 1 depicts a three-level inheritance code structure by role definition. The first level is a base class which is composed of all functions of the IP and variables that can activate each function, and all the verification components required to activate the target IP, including VIP, interfaces, and so on. The second level class inherits the first and is responsible for enabling the function of the base class. The third level class inherits the second and connected the functions which are generated in the second level class to implement design and test bench information, for example, target CPU, address map and register handler, and so on. This implies the first and second level classes can be fully used without many modifications, while the third level class needs to be modified according to the target chip configuration. And the figure 1 is a three-level inheritance code structure to maximize the code reusability. Figure 2 shows the implementation example code for a three-level inheritance structure. The target IP is a UART buffer. Let's assume that a target SoC has 4 instances of UART, and each UART has functions like TX. So the transmission and RX receive. As shown in figure 2-A, the first level class code implemented the S variables as the SB tasks for UART operation. An S variable maps to an SB function and task, and each features a few structure that control the variable specific operation. For example, enabling m underscore UART underscore TX func is variable executed the task UART underscore TX underscore operation underscore test. So in addition, this class includes all the handlers required to be stimulate and monitor the UART function. And this example verification IP, VIP, which acts as a counterpart of UART, an interface to monitor the values to be checked. And the register model to program the UART are included. Please note that the actual control of the variables is implemented in the second level class, while the handlers are mapped to the third level class. To add new functions or change existing functions, it works only in the first class and resulting in the localization of the code change. Figure 2b is the second level of class code. In this example, the classes corresponding to TX, IP underscore USI underscore UART underscore TX underscore SEQ underscore C, and RX, IP underscore USI underscore UART underscore RX underscore SEQ underscore C, and UART functions are declared respectively. These classes are embodied into a sequences to perform the TX-RX operation by enabling the variable declared in the first level class. As a result, the purpose of the second level class code is to build a sequence, a class library to be used to make complex and composite test scenarios. As shown in figure 2-C, and the third level classes code maps on the sequence classes defined in the second level code into the target product by using the macro method. As assumed, the two function sequences are configured for 4 instances, resulting in 8 operation sequences. In this class, and the handlers of the interface, the register model class, and a VIP sequencer class defined in the first level class are also connected according to the product configuration. The code changes that occurs according to the product configuration, such as the number of IP instances, register model, and the interface are connected to the hardware hierarchy, and so on, could be localized in the third level class by using the 3-level inheritance code structure. The code change for each target product can be minimized, and the first and second level code can be fully reused without any modification. So A is the first level class of the UART, and B is the second level classes of the UART, and C is the third level classes of UART. The figure 2 is the example of the 3-level inheritance code structures. As explained earlier, the SoC level test scenarios are implemented by mixing the IP-specific and system control operation. For example, the transmit and receive operation of the UART should be combined with the system reset in the middle of the transmission and or after the completion of the transmission. The easiest way to implement any system control operation is to directly insert the code into each IP-specific operation code. Although it is a very straightforward technique and has an advantage to early bring up the test scenarios, it has fatal disadvantages. As the number of the verification entity increases, the same code should be implemented into each target, resulting in the code size increase, and the old code cannot be reused because the system control operation is very product dependent. To overcome this limitation, the system control code be separated from the IP operation code and implemented as a form of the standard library called the command task shown in figure 3. Now, as each IP operations scenario calls the functions from the common task library, the system functions can be reused over different IP operation. However, this approach still has a limitation that they can be only reused for the same SoC product. They are still hardware implementation independent and should be modified only they are used in different products. To maximize reusability, we propose a method that uses application programming interface API, a software programming technique, by encapsulating the common task among the different products and designing the custom APIs so that for a general purpose system control function, the hardware-dependent portion of the code can be hiding, and the same code can be reused by the different hardware platform. so the scenario developers can maintain them consistent when they use the system functions during the implementation of complex test scenarios. So the figure 3 present an example of the reusing two system control functions, system reset 1 and reset 2. For known end product which has m IPs, initially each system reset 1 and system reset 2 are configured differently inside each test scenario. They can be converted in the form of the common task for each product and can be reused within the same product. So finally, the final two system reset common tasks are merged into a system reset API which has an argument for reset kind. System reset kind for an end product. The API can be reused for all products. Of course, their implementation of the APIs is product dependent and requires modification. Nevertheless, the scenario developers can use the same API without specific information of the hardware implementation. So this is the figure 3 is called the structure of the system function API. So table 1 shows an example on part of the system control function managed using an API. Each system function can be called with a predefined argument. Suppose the target SoC is equipped with the power on reset (POR) and the two watchdog timer reset. The hardware reset control API can be used like control_hardware_reset (POR), control_hardware_reset (WDT0), and control hardware reset WDTI. Table 1 is an example of system function APIs. Once the IP function sequences are implemented by using the proposed 3 level classes and the APIs for the system control functions are ready, the complex design level test scenarios can be written easily by combining them together. At the same time, the major portion of test code can be reused without any modification. Section 3 is increasing the efficiency of complex and composite scenario development. Generating and performing the complex and composite test scenarios can ensure better quality SoC verification, and the high efficiency of developing test scenarios definitely shorten the SoC verification TAT. This section describes how to increase the efficiency of scenario development so the test scenario is implemented after a set of the unit sequence is ready. Unlike the scenarios that consist of only one sequence, complex scenarios that consist of multiple sequences are usually developed using a framework. So the figure 4-A shows an example of a framework for the 3 sequences that operate in serial order. A scenario developers can freely compose with 3 sequences using various IP functions and system tasks depending on the requirement. For instance, test scenario N is composed of the IP2 function, IP2 function, IP5 function 1, and system task 3 in figure 4-A. Here we cannot create scenarios that have more than 4 sequences or more than 2 sequences operating at the same time. The additional scenario frameworks are required to develop a more complex test scenario and to meet a target coverage for function verification quickly. As the number of verification entity and the system complexity increase, the number of scenarios also increases because a lot of combination become possible, or the number of test scenarios may not much increase if we can make a well-organized scenario framework that can cover many sequence combinations at once. But still, it has a limitation to reach the target coverage quickly, as we have to go through these steps of configuring test scenarios, creating the frameworks, and putting sequences in them. So we propose a new scenario development flow to overcome it and further efficiently develop diverse test scenarios. The most important difference compared to a conventional flow is that a scenario developer can abstract a test scenario. When they describe a test scenario, a high-level abstraction, the generating the framework, and the mapping the sequence that happens at once. The scenario developers pick sequences from a respective repository containing IP function sequences and a system AIPs. and combining it depending on their requirement as shown in figure 4-B, and so far they do not have to consider a form of the framework at all. The framework, including the sequences, can generate using the scenario sequence description in the configure in this flow. Scenario developed is much easier than the before because the even complex test scenarios can be also generated if they just abstract the sequence flow what they want to cover. Furthermore, it is possible to create a much more complex composite scenarios which is composed of arbitrary sequence order. The current scenario development flow. Figure 4-B is a proposed scenario development flow. To implement this, we define a metadata syntax and developer's interpreter, writing a form of the metadata containing the order of sequences. Then the interpreter reads it and generates a framework accordingly. The metadata consists of the sequences which come from the third-level classes and system function APIs and operators, and the first and second are described in section 2. The operators act as a symbol that describes the sequence order. For instance, the now U line means serial order, and percentage parallel operation, and each sequence is which is divided by the semicolon and within the braces, and with the operator sequentially. The left side of figure 5 shows the example of metadata to construct a complex scenario. The sequences sequence A, B, D, and E are selected from the third-level IP classes, and task 0 and task 2 are chosen from the system function APIs, and combining them. Scenario developer write a form of the metadata. The sequences, sequence B, C, D executed sequentially, and sequence E and task 1 execute at the same time in the example. Like this, metadata makes it easy to generate a framework within the arbitrary sequence order. On interpreter inputs metadata automatically generate UVM test code. The interpreter created a framework to follow the UVM test syntax like a declaration of classes, tasks, and variables, and generate test scenarios according to the sequence order described in metadata. The right side of the figure 5 shows automatically generated UVM test code by interpreter. Figure 5 is using the interpreter to generate a complex and composite scenario. Figure 6 shows an example of creating a test scenario using the third-level IP classes of the UART and the set of the system function APIs is described in section 2. And the purpose of the test is to guarantee the functionality of the parallel operation of all UART instances, and the second is sequential operation of them, and the third is the system level and block-wise reset in the middle of the UART operation. Based on the predefined metadata, the required functionality and their orders are easily implemented as shown in figure 6a. The interpreter automatically generates real UVM code after taking the metadata as an input. Figure 6b generated UVM code. So this example demonstrates that any complex test scenarios can be easily defined using the metadata without any background knowledge on UVM language, and it can be implemented automatically, resulting in the fast bring up without any error typically incurred in human coding. Examples of the metadata. The next one is the figure 6 example of creating test scenarios using the proposed method. As B is the example automatically generate UVM test code. Section 4. Experimental result. This section describes the result and effect of the proposed code structure and the scenario generation flow in the previous section. Two automotive SoC products which have been designed and the same architecture platform have been verified. The second generation product target is a higher performance and is infused with increased complexity than the first generation one while having the similar functionality. The first generation of product was originally verified using the conventional method of the existing test scenarios have been reorganized into a proposed 3-level code structure. So the test scenarios of the second generation products are created by the reusing the first and second level classes of the code. Table 2 shows the number of the UVM code lines for each level of the classes consisting in example block. Block I, the result demonstrated that about 86% of the code in average belong to the user first and second class. The test scenarios can be implemented after modifying the remaining 14% of the code according to the target SoC configuration. Table 2 amount of the test scenarios code for 5 IPs in block I. Okay, after the third level classes for IP-specific operation and the common APIs for various system tasks are ready, a set of the complex and composite test scenarios have been automatically generated by using the proposed scenarios generation flow. To check the efficiency of the proposed approach, we compiled the number of the test scenarios to cover the target block 1 to 4, which are integrated to product as shown in figure table 3. The test scenarios for the first generation product have been implemented based on the conventional predefined framework. So those of the second generation product have been generated after defining a set of the arbitrary sequence framework using the metadata. The result shows that the same coverage can be reached with only 13% of the total number of the test scenario, and 89% of the test scenarios can be reduced. Table 3 is the number of the scenarios to do the 4 blocks for 2 generation product. As a result, the UVM, the code making up the total test scenarios, can be classified as categorized and reusable class of the code, the first and second class of the code. Second is non-reusable class of code. The third class of code in a repository, and the third, the test scenario class, which are automatically generated by the interpreter. So the table 4 represented the portion of each code and category. The result shows around 88% of the total code can be fully reused without any modification and automatically generated. By editing the remaining 14% of the code lines, and all test scenarios writing step can be completed this can dramatically increase the productivity of the efficiency of the verification processes. The table 4 is code amount of the test scenario for blocks and the second generation product. In conclusion, it is possible to secure the many IP functional operation test scenarios at a very early SoC design phase and increasing the maturity of the design with a short period of the verification process. The diversity of the test scenarios combining lots of sequences and tasks also have to find barely any complex design bugs and complete the whole verification process within the given verification time budget. The summary. This paper is intended to reduce the verification time by optimizing the UVM test code structure and improving the composite and complex scenario efficiency. And we propose a three-level inheritance code structure to maximize code reusability and a new scenario development flow that contains the scenario defined in the form of the metadata and interpreter to automatically generate the test scenarios using defined metadata. Experimental result demonstration 86% code reusability when applied to the 2-generation product, and show a decrease in total number of the scenarios up to 87% while maintaining the same verification quality compared to the product that did not use the proposed scenarios to develop the flow. The acknowledged. We will references. Today I read this paper from the DVCON2023, the strategy to maximize reusability of the UVM test scenarios in SoC verification. Thank you for your time. See you next time.